So, hi everyone. Welcome to our lecture 18 or 2, so depending on the count. Okay, so today the topic is convergence rates and worst case analysis. So we'll mostly talk about the first steps in worst case analysis, although it could be more like the second step, because we got the first step to show you the methodology in general yesterday. So here we're going to talk about convex problems now. And I see that you worked on the material from yesterday. You had many questions. That's nice to keep asking questions, and I'll do my best to answer. And maybe and also of course Lionel and maybe also Max steps in case anybody they're quicker than me in this. Okay, so convergence rates and worst case analysis. So when we continue the methodology with these annoying functions. So what we do today is only work on these annoying functions for 2 cases, and then tomorrow we'll proceed and work on the last case, and then not tomorrow but the next week on Tuesday, and next Wednesday we will start with algorithms. I think it's only up to next Tuesday, next Wednesday, where we start with the algorithms and see if they're going to match up the worst case bounds we get. Okay, so let's move into the case where now we're in the case where f is from Rn to R some extended real numbers where infinity is allowed, convex and L Lipschitz. So not the gradient is L Lipschitz, but only the function. So the function may have kinks. That's allowed here. So, and now here comes the theorem on the worst case analysis. Theorem 18.1. So what is the worst we have to expect? And the theorem goes like this. For every k, which is between 0 and n plus 1, there exists first a function f, which now depends on k. It's on from Rn to R. Actually, it's finite valued, so I can just leave that off here. Convex L Lipschitz with minimum. So we need that for the proof. The minimum should denote the minimum by f k star. And this should be attained at some particular value x star. At some x star, and this x star has also a known bound. Also an oracle for this particular function that gives some p for every x we ask it for. So this means for with this function fk there comes an oracle, and when we ask for one subgradient we get one, but we can't choose which one. So these 2 things such that every sequence xk which fulfills our assumption on the algorithm, which means also I forgot to introduce a starting point. So there exists this and that, but also some starting point x0, and then every sequence which fulfills that xk is contained in x0 plus the span of the first k gradients, so p0 up to p k minus 1, fulfills the inequality that the function value which we get at the end, so now at the kth iteration, the distance to the optimal one which we would like to have is bounded from below by some constant. The L is the Lipschitz constant of the function, R is the upper bound on the norm of the minimizer, and now come to divide this by 2 times 1 plus square root of k plus 1. Okay, so that means, however, we can cook up some method which moves to the directions of the subgradients we see given by our oracle. There's always a function such that we will, after k steps, will not be better than this bound here. Okay, so so this is kind of an unavoidable lower bound for any method to minimize the convex Lipschitz continuous function, which only uses directions of subgradients. With only this information, you can't do better in the worst case than that. So on the other hand, there may be algorithms which may solve some particular problems much faster. Sure, that's this is not that's not excluded here by the theorem. But if you do any method which does something like this, then you have to expect not to be faster than that. Okay, so let's see how the proof goes. So the proof goes as before. We cook up the function and then show that we can do. Yeah, it's actually this time we don't have to fix the algorithm. It's not really necessary. We can just give the function which basically annoys all algorithms, which goes like this, no matter how. So and just give right away, start right away. So we fix some constant mu and gamma, non-negative, and we choose them later. So for now we just take the two positive constants, non-negative constants. Actually, I just see that we need them positive anyway. And so we define fk, a function on Rn, as follows. Two terms, one is gamma times the maximum of the first k coordinates, so 1 smaller equals I smaller equal k, and plus mu over 2, the 2 norm squared. So this is a function which is kind of difficult for all methods which move into directions of subgradients. Yeah, I don't know. For me, for some reason, it was hard to visualize how this function looks. And here I have visualization for you. I can show you the level lines of the function for some values of gamma and mu. So here, that's the level lines for this function here. So this maximum kind of has level lines which just go like that. So for example, all the vectors along that line here, the one here and the one there, they have this first term here, this max here. You can see this this max here equal to 1, and we multiply by gamma, and then we add a little bit of a paraboloid on top of this, which kind of curves all the lines, and then in the end the function looks like this. So you can see that the minimum seems to be like here, a little bit in the negative orthant. But also, since this here is the diagonal, it lies on the diagonal, so it has all entries equal. That's how it looks, and we will calculate the minimizer in a second. So, and if I now make this mu larger here, I make these lines curvier and curvier. And if I drive the gamma to 0 and the mu stays constant, then I will end up with a function which just have circles around the origin. And if I turn that term here up, so these circles kind of open up in this direction, or kind of get deformed into this direction. Okay, that's the annoying function, and now let's prove that it really is annoying for all subgradient methods. So first, let's calculate the subgradient. And one more thing is that these this is only for the first k coordinates, but since I only can plot 2 dimensions, so and k equals 1 doesn't really tell you anything, I chose k equals 2 as well. So what's the subgradient or the subdifferential at some x? It's not totally difficult to compute because, well, the subgradient of the 2 norm is the usual gradient. So here behind we have some mu times x, and actually since this function is continuous, everywhere subgradient sum rule applies, and we know that it's like this. But what's the subgradient of that? There's also a rule for that. So the subgradient of a max of convex function is the convex hull of the subgradients of the individual functions over which you take the max, but only of the ones where the maximum is attained. So in this case, and the subgradients of the individual functions here is always just the respective standard basis vector, so the canonical basis vector for xi, linear function xi, the subgradient is just the unit vector ei. So this gives us that the subgradient of the first term here is gamma times the so-called convex hull, conv, of all the ei for some I in a set I of x, and this I of x is the set of indices or the j's which are among the first coordinates such that xi is equal to the max, xj is equal to the max of ai. So, so for example, if the vector xi just has one entry in the, let's say, second component, then the subgradient of this max here at this point is just gamma times the second basis vector plus mu times x. But if the maximum is attained at different points, so for example the vector looks like 1, 1 and then comes 0, then the subgradient is larger, it's really a set. And these are the points in the figure where we are at these kinks here, right, where two entries are equal. This is at these points, and you see that there's a kink, and then you see that the subgradient is actually really multivalued in that case. And it's actually the convex hull of the respective new basis vectors. Okay. So what is clear is that this function here is Lipschitz continuous on any ball because it's continuous on a ball. So fk is Lipschitz on any ball b rho of 0 because it's because it's continuous there. It's Lipschitz on a bounded domain. So it's it's even more than that. So it's anyway, so it's not difficult to see that, and I think we're going to compute there's the calculation here. So we calculate the Lipschitz constant here. So for a Lipschitz constant, we should consider the difference of function values and estimate it. And what we do is by a subgradient inequality for any if we have some pk of at the point x, which should be a subgradient of fk at x, then we can use the subgradient inequality here and say it's bounded in this direction, like pk of x times y minus x. And here we just use Cauchy-Schwarz and get pk of x times y minus x, and then c. That's already nice, so we only bounded the distance, so we could also do it like this if you like. So we can do this by swapping the roles of that one here in the end. So you already have a distance over there, and we only need to estimate the size of this. So, but this is not so difficult. This is convex combination of unit vectors here. And we have this x over here. The convex combination of unit vectors has norm at most 1. So we get here the constant gamma, and this may have no norm up to rho, so plus mu times rho. So we can take L as gamma plus mu times rho. So we were going to choose this gamma and the mu and the rho in the end. And so such that our conclusion in the end holds. So that is now done. This f is Lipschitz, continues on a ball of radius rho. Nice. So let's, what's the minimizer? So we calculate the minimizer now. So how does that look like? So, which means you want to solve the inclusion 0 as a subgradient f k at x star. If you look at that, I would say you need some careful inspection just by looking at it hard enough. How can that be that some x star so that this gives you 0 here. So you see, this is the convex hull of unit basis vectors. So this is always a vector which has positive entries between 0 and 1 in the first maximally the first k entries. So you see that the entries of x have to be negative actually. So, and if you stare at it hard enough, then you will see, and you already know, that the entries of x star should be all the same for the first entries, it holds like so. This x star has the following entries. So the ith entry is either 0 or has the value minus gamma over mu times k, and this holds if I is between 1 and k or 0 elsewhere. So this optimum value, the minimizer, is at a vector which has this entry here for the first k entries, and after that only comes zeros. And if you plug it in, you'll see that it works, that it checks out, that this actually gives 0 always. Okay. Good. So that's the minimizer, and then you see it's actually slightly negative in all entries which are not 0. So let's calculate the norm of that. So let's calculate the norm of this x star. Two norms. Here also this has been two norms. So probably that's the confusion here. So what we need to do is, so we have the max here, and we have the norm squared here, and the subgradient of the norm squared is this, and this was not your question, but what is the subgradient of this? And that is the set now, and this is the convex hull. So this convex hull already is the subgradient of that term. It was probably a little bit fast, and it also probably takes a little while to see that. Maybe I can draw a little illustration. So these are the axes. Let's say we have n equals k equals 2. So we are in R2, and we just consider the function the maximum of x1, x2. So this function has level lines which look like this. So these are the level lines. So along these lines, this function here is constant. So here, let's say here it's constant 1, constant 2, constant 3. At this line is constant 0, there it's constant minus 1, constant minus 2. So the subgradient, or the subdifferential, kind of gives all the vectors which points into the direction where it goes up. So for example, at that point here, that is the only subgradient. But this point here looks like it has a large entry in the second component and the small entry in the first component. So the entry in the second component is larger. So then the subgradient is just the second basis vector. At these points here, where the first entry is larger than the second, because it's below this diagonal here, the subgradient is that one and is the first basis vector. But at points like these, where both entries are equal, so this vector here may look like, let's say it's vector 3, 3, both entries equal, then this is a subgradient, but also this is a subgradient, and also this is a subgradient. So in kind of all these vectors along which point towards this line here. That's the convex hull of these two vectors, all the vectors which point to that blue line. That's the subgradient in this case. Okay, so this is E2, this is E1, and this is the convex hull formed by these two vectors here, the blue line. So this is here that's the subgradient of this function down there at this particular point. Okay, good. I hope this helped a little. Okay, calculating the norm is not hard. You just need to square all the entries. Oops, I'm a little off screen. You need to square all the entries and sum them up. So there are k entries of that type. So we have k times this number squared, gamma squared over mu squared k squared, and then take the square root because we take the norm, so 1k goes away. This gives you gamma over mu over square root of k. Okay, that is probably straightforward. And also we need the optimal value, fk star. Yeah, we just plug this in our function. So the function is is given here. So the maximum among the first k entries is this -1. So we have this minus gamma over mu k plus this gamma squared, because we have gamma times the maximum, we got gamma squared, plus mu over 2 times this rk, which is squared, the norm of x star squared. And if you do the math and evaluate that, you get this is minus gamma squared over 2 mu k. Yeah, that's how, minus gamma squared over 2 mu k. That's what you get, because if you square that, you get gamma squared over mu squared times k. 1 mu cancels, you get a half. This gives that. Okay, these are our two things. It's the norm, that's the optimal value. Okay, so now let's see what any algorithm which moves into subgradient directions can give. And that is now, that's now nice. What can happen here? That is kind of where the magic in the proof happens. So now it's important we initialize at 0, at the vector which is all zeros. And so our aim is to show that any xk, let's say xj, is of the form we have entries here, but in the end we only have zeros. And this here are the first j entries. So this is what we want to show, that only the first j entries can be non-zero, no matter how we do, as long as we only move in the directions of the subgradients. Okay, so we do this by induction. So j equals 0. That's clear because the vector x is only zeros. So and now comes so that's the first step. And now comes the step. What can we do? And now it's important that we can also choose the subgradient as bad as possible. So the subgradient at x equals 0. So this here. So we take a bad one and there's a bad one. So what can we do at x equals 0? Let's have a look at the function. So all entries of x equals 0 are the same. So the subgradient here is the full convex hull of all the first k basis vectors, and then we add a 0 here. So we pick one, and we pick p0 as gamma times the first one. We could also have taken the second or the third one, but this would not work for our proof. But our claim is it's that the oracle is part of the annoying function. So and then it's clear if we have x1 is then of the form x0 plus the span of p0. So it's kind of alpha times e1 for some alpha in R. So because this is 0, this is the first multiple of the first basis vector, so this can be also only a multiple of the first basis vector. Okay, now assume, so this was actually not necessary, now assume our claim holds for some j. So if the claim holds for some j, then what subgradient should we take? And again, if the claim holds for this xj, it only has non-zero entries in the first j coordinates. So since they all be negative, so it may be that these are all negative, there is a possibility that these here are the larger ones and the same ones. So we can always take the pj, which is of the form, of course, mu times xj, because this was the latter part of the subgradient here. We always have that term. And for this term, you can also have something like gamma times ei star, and this I star has to be smaller than j plus 1. So it may be that the largest entry is among the first ones, if one of them is positive, but if they are all negative, which is not excluded, then we can take the j plus 1th entry here. And this is the worst we can get. But so we could take larger indices, but we don't do it because we want to have an annoying oracle. Okay, so, and this also already proves the claim, right? Then we have that xj plus 1 is still x0, oh no, it's not, it's in x0 plus span of p0 to pj, but this is yeah, and so this can be at most the I plus 1's entry, so it's again of the form here we have stars, here we have stars, and so the last one which you could take, this would be the j plus 1's, everything else is still 0. And that proves the claim, and so the claim follows because we can choose this bad subgradient here. This bad subgradient, so we may have even worse subgradients in case the maximum is assumed in the first k entry, the first j entries. But if they are all negative, then we have the maximum assumed all in the back ones, and then we choose the bad one, which is just the j plus 1th. Okay. So what does that say? So we've proven that here. This is now done, and now this says that if we calculate that, what does our objective gives after I iterations? Of course, it's bounded from below by only taking the max, so I just omit this ki. There's typos here. Yeah, this should be, sorry, this should be j. Oh, we have to make a note. So there's plus the norm squared, but I just leave that out, so I make it smaller. This is actually always larger than 0. Because there's always an entry 0 involved, right? We take the maximum over the first k entries, but if I is smaller than k, there's always at least one 0. So the first k entries are not all negative. One of them is 0 still. So the maximum may be much larger, but it's not smaller than 0, that's for sure, because there's at least the kth entry which is still, so k is strictly smaller. The kth entry is still 0. Okay, so we know that our function, our objective only gives something which is positive for the first k minus 1 entries, iterations, but the overall objective value is that negative. So that looks good. So we know that in the beginning we don't improve beyond 0, but in the end we have to reach something which is this much negative. So now the rest of the proof is just choosing the constants. And so I just show you how you can choose them and then calculate that everything works out. So choose. So how do we choose? So we choose gamma as square root of k times L over 1 plus square root of k. Looks weird but works. And we choose mu as L over 1 plus square root of k times r. Okay, so why do we do that? Because then everything checks out. So then we get that the optimal value so we can just copy it from here. You can copy it from there. Gamma squared over 2 mu k, and this, so it's minus gamma squared over 2 mu k, and this evaluates 2 gamma squared that, and so it's a little bit of to do this. So for example, this 1 plus square root of k almost cancels, but only 1. So in the end, you get LR divided by, so minus LR divided by 2 1 over square root of k. And you also have that the difference from the initial value, which is 0, to the solution, is then we also calculate this is gamma over mu times square root of k, and if you plug that in, you see that this really is actually R. So, and Lipschitz constant, so we had calculated this in the beginning, this was mu times R plus gamma, and if you check that out, what this gives you, if you take mu times R plus that, you will actually end up with L. So, and that's actually what we need, right? This is what we wanted to show. We wanted to show that on a ball with radius R, there exists a function with Lipschitz continuous with constant L, such that the iterates give function values which are this much away from the objective value. So the function values we get are positive, and the function value you want to have is this negative one, so that the 0 minus that is at least this value here. And that was the full proof. Okay, so somehow all the calculations are straightforward here. This is nothing too difficult what we're going to do here. But I think the proof is difficult. Because the statement is difficult, and also all steps is not obvious why it's going to work. In the end, you see it's going to work, but it's still a little bit of magic going in. But the key idea is to find something such that you have control over the non-zero entries in all the iterates. Because of the iterates, you don't know too much. So our assumption only says that it fulfills this inclusion here. That's only in the span of the subgradients plus the initial value. And so that's the best hope which you can have, that this is a set which you can control somehow. And this is how the proof worked. We designed the function and the subgradient in a way that we have control over this set here, namely that it only has vectors such that the first k minus 1 entries are not 0. Yeah, the first k entries are not 0. That's the main ingredient of the proof, and the rest is computations. So granted, they are not so simple, but the rest is computations. So the conclusion is, maybe I should write it down here. So the take-home message, conclusion, no method, and with no method I mean no method fulfilling this assumption here that it only uses subgradients and only moves in the span of the first subgradients, performs better than giving it the kth iteration minus the optimal value, decaying like 1 over k in the worst case. So of course there are methods which are better for some functions, sure, but no matter what the method is, there's always one function such that you can't beat something like this. So the constants may be different, and we have explicit constants in the in the theorem, but I have no idea if they are optimal. But what I most care about is this decay like 1 over square root of k. Okay, and one says the iteration complexity of convex optimization of Lipschitz functions on bounded domains is 1 over square root of k. So that's the thing that this is what you can expect. So you can do. You may run into a situation where you really see this convergence rate, and from my experience with non-smooth optimization and subgradient method, it happens. This is kind of typical, actually. They usually don't do much better than that. Okay, that was the case of convex and Lipschitz continuous. So no smoothness involved, we only have subgradients, and this is part of the problem, right? You only have subgradients, and subgradients can point to directions which are not really good. Yeah, that's probably how it should be, how you should see that. Okay. Yeah, so I'm not sure. I think there's room for improvement. So, for example, if you consider that you always are able to choose the subgradient with minimal norm, then I'm not sure if this result still holds. I don't know. I'm not sure. I don't know. Okay, so now come to the case where f is differentiable. It's convex and L smooth. So now next step is f goes from Rn to R convex and L smooth. Good point. That's a very good point. Is k an arbitrary step in the iteration or the length of the whole iteration? No, this is the latter. It is in the endpoint. But it holds for all iterations up to the k. Yeah, that's good. So we only proven this for the endpoint. No, they only stated it for the endpoint. The proof works for the first k iterations and not beyond that. And beyond that, I actually don't know. We can't say anything. In the next step, we may be there. But kind of the conclusion is because you can't. Because this works for every. This works for every k up to dimension. Why is dimension +1? Probably only dimension. I don't know. At least for up to dimension, we can do this in any dimension. So you can get with k up to n. So for the first n iterates, you can't do any better than that. So after that, it may happen that the subgradients span the whole space, and then in the next step you may be done. So this result is basically not really interesting if you work in 10 dimensions or something. Because in 10 dimensions, then you do 10 steps, and then after that you may have accumulated enough subgradients that they span the full space. But it's interesting. And performing 10 iterations for 10 dimensions, it doesn't take you anything. You can just even do it on paper sometimes. But if the dimension is large, and thinking about machine learning applications, this dimension is ridiculously large sometimes. So it's the number of degrees of freedom over which you want to optimize. Sometimes it's in the billions. So you definitely don't want to do a billion of iterations. Nobody can afford that. So, but for the first number of iterations which go up to the dimension of the space, for this you can't do better than the lower bound. So, but technically it's true what you said. So it's really that it's only for the k up to the dimension of the space. But we consider, so this is most important in the case where the dimension of the space is very large. Then this is still meaningful. After that, we can't say anything. And this is kind of how the results go also from that point on. But it's a very good question, actually. That's very nice. That is really a point in the proof which you can't go beyond the space dimension with this kind of proof technique. But also, this assumption then kind of breaks down. If you have your more vectors than your space has dimensions, it's really possible that they span the full space. And then after that, the xk, this set has to include the minimizer. So this is kind of the end of the story. If these span the full space, you cannot exclude the possibility that the next xk can be the minimizer without any further assumptions. Okay, great. So here things change. If we are L smooth first, we have more inequalities to work with and prove that some algorithms actually work. Also, we don't have the freedom to choose bad subgradients because some functions now smooth. We have always fixed subgradients. Oh, and I forgot something. For the people who attended the first part of the lecture, we showed actually that the subgradient method achieves like 1 over square root of k. So there is a method which does that for every function provably with different constants. They are larger but not ridiculously large. So on the one hand, the situation is now nice. For this class of method, we have an algorithm which one can implement, which matches the worst case bound up to constant. But on the other hand, the worst case bound is bad, so the situation is still not satisfying. And I think Nesterov writes in his book that the conclusion should not be that the subgradient method is a good thing for this class of problems, but that the class of problems is too large, such that there could be a good algorithm for the full class. That's his takeaway, and I agree. So minimization of merely convex Lipschitz functions without any further assumptions is a kind of hopeless business if you really don't know anything more than that. Okay, and if you want to be able to solve even the worst problems in this class. So here things change a little, but not that much. So what is this is our function class now, and our assumption is again that the xk is in the set initialization plus the span of the first k minus 1 gradient. So and g is the gradient is equal to the gradient of f at x. So these are the first k gradients that you see. And we call these methods which do this first order methods. So any method which fulfills this will be a first order method because it only uses the first order derivative of the function and then does some algebraic steps with these directions it gets. So what is the Hanoi objective here? So the Hanoi objective goes like this. We fix an L, and again we fix a K, because as we already discussed, going beyond the space dimension is not really meaningful. And we define an Fk from Rn to R by I write it down two times. First, it's now here in in entries of the vector. It's L over 4 times 1/2 x1 squared plus the sum from I equals 1 to k xi minus xi plus 1 squared plus xk squared. Oh sheesh. Oh no, it's correct. There goes parentheses around this guy here, and in the end we subtract x1. So that's the annoying function, and it looks, I don't know, I find it not so simple to digest. So but here comes another way to write it. It's the same as oops, where is it? L over 4 times 1/2 norm of dx for some matrix I will give you in a second, minus the inner product of the first basis vector with x. And the d is the matrix which is of the following form. It has minus 1s on the diagonal, 1s below, and everything else is 0, 0, 0. And these here are the first k columns, and these here are the first k plus 1 rows. And overall the matrix is n by n. Okay, so if you check now carefully what this does, if you multiply this matrix here times the vector x, the first entry of dx is negative x1, and you square that, and that's this one. The second entry in dx is x1 minus x2. You square that, and this is this entry here. And the last entry here, the kth entry, the k plus 1th entry, the k plus 1th entry here is just xk, because this sits in the k column here, and this gives that, and this subtracts this. So I find this much simpler to work with. Okay. Okay, nice. So, and if I know this this representation of the function, it's pretty simple to calculate the gradient. It's just, of course you get an L over 4 here from this constant, it just stays there. This here gives you d transpose d times x, and this just gives you the first basis vector. Okay, and also the Hessian is straightforward to compute then, because this is now linear in x, the second derivative, so the Hessian is L over 4 times d transpose d. Okay, so we would probably, and we call this guy here A. So how does this A look like? So A is d transpose d. How does this matrix look like? This d transpose d, I know it's a little bit of algebra, but so basically what this does is to form first order differences, and d transpose also forms first order differences, and if you careful inspection shows you that this method gives 2 on the diagonal, minus 1 on the first upper diagonal, minus 1 on the lower one, and still zeros here, here, and here. And if I'm not mistaken, these are the first k columns and k rows, and it's still n by n. That's how d transpose d works. Okay, and I think we're at half time of the lecture, so I need a short break because it's getting really warm in here. And we see you back in 2 minutes. Okay, so short break, and 2 minutes we go again. Here it is. Okay, here I'm back. Okay, so and as before, we want to show that this function is now it's bad. So first we need to check all the assumptions. So we need a function which is convex is clear, right? So this is a quadratic, and this is linear. That's so convex plus linear and also minus linear. That's convex, so we can check that box. We need to show it's L smooth. So and you ask for that in the chat. So what is an example of an L smooth function? This is one. And then we also want to know where's the minimum and what is the minimum value. Okay, so to compute the smoothness, actually what is enough for L smoothness if the Hessian is uniformly bounded. So the norm of the Hessian, which means the largest eigenvalue here. Yeah, and so what we do is we would like to calculate, oh, there's a typo again. There's f prime prime, which should be the Hessian. So we would like to calculate that guy here times s for some vector s. So if you can bound this from above by a constant times norm s squared, then this is an upper bound on the Hessian. So we know, for one, that this is actually equal to L over 4 times the norm d of s squared, because we have here d transpose d, and one d moves over here. So this is already positive, and this also shows again that f is convex. So I skipped this calculation here. It's it's not terribly hard, but it's also not really fun to do that. So you calculate this here, what this gives you, and then some estimation shows you that's actually smaller than L times 2 norm squared. Yeah, it's not, basically it's because the row sum is 4, more or less. The largest row sum is 4. So this shows you that the Hessian of f at any point x is bounded from above by L times identity matrix and bounded from below by 0. And this shows, or fk, so that was fk, f is convex and L smooth. You could also prove the same thing with the gradient. It boils down to calculate the norm of A, into the norm of d transpose d. And this is L. Okay. Good. So now where's the minimum? So where's the minimum? I formulated this as a proposition. It's 18.2. Fk has minimizer, unique, I forgot that, unique minimizer x star, and the ith entry of that is either 0 if I is k plus 1 up to n, or it's the value 1, yes, thank you, that's fk, great. The entry is 1 minus I divided by k plus 1 if I is 1 or up to k. So that's the minimizer. And optimal value is, so this is denoted by fk star, which is fk of x star, and this gives us L over 8 times minus 1 plus 1 over k plus 1. And we also can calculate the norm of that x star, 2 squared. This is not larger than k plus 1 over 3. Okay, this is what we're going to show. And so what I know, the notation does not show you that, of course, the minimizer here also depends on k. But there's not more space for another index here at the x star, so I just call it x star, but technically x star also depends on k, and we're going to use this the next lecture. So because we can't finish the full analysis of this case in this lecture, we have to finish this next lecture. So the x star also depends on k, but okay, I can't include it in the notation. So okay, how do we do that? How do we prove this? That's basically calculations. So because the minimizer fulfills 0 is equal to the gradient of fk at x star. And this is just L over 4 ax star plus, minus ei. So our x star has to fulfill ax star equals e1. So let's write this down. So this equation A x star equals E1 is just the same thing as, so the A was 2 over here, up to there, minus 1's over there, and down here. Then there comes zeros, times x1 up to xn shall give 1, and then comes zeros. That's the system of equations we need to solve. Okay, so what do we observe? First we observe that the last entries here, or there, they have to be 0. So they actually... Actually, the minimizer is not unique. There are more minimizers. So this uniqueness here is wrong. But it doesn't matter. That's actually not the point of the proof. So we don't need uniqueness. So we can take x star. So these are the star entries. X star I equals 0. You mean with these values here? This is what we're going to compute. But probably your question is something else. So if you ask for these values, I'm going to show in a second. So I'm just working on that. Okay. But so if you mean something else, then please ask again. So what I want to show you, so the last k, the last one, so after the kth one, they can be 0. For a equals k plus 1. Because so they only hit the zeros here in the matrix vector multiplication, so we can take them to 0 as well. It works. So now we write down the first equation. So the equation 1, so the first line of the system. So the first line of the system gives us 2x1 minus x2 equals 1. So, sorry, wrong window. This gives us, and I wanted to write it like what? I wanted to write, this gives us that x2 can be written as 1, no, it can be written as 2x1 minus 1. That's what we get out of the first equation. And omit the stars here because I have to write a lot of stars then, and it just doesn't help. Equation number 2 would be minus x1 plus 2x2 minus x3 equals 0. So if we plug this for x2 in here and solve, so if we use this formula for x2 here, so we place it over there, and then we get minus x1 plus 4x1 minus 2 minus x3 gives 0, and if we solve that, because you have here minus x2 minus x1 plus 4x1 gives us 3x1. In the end we see solving for x3, this is 3x2 x1 again, sorry, x1 minus 2. So, and if you now do this in the next, and then the next, and the next equation, so you will see, so moving on to equation 1, equation I, you get that xi is actually I times x1 minus I minus 1. So this kind of the pattern goes through until the end. Not until the end, but until I is between 1 and k. For all the rows which look like this, this is the case. And then, no, k minus, no, this holds for the I. Yes. And finally, we also get the equation, so in the last row, which is non-zero, we get minus xk minus 1 plus 2xk is equal 0. And if we have formula for these two things, so we plug in the case for k and for k minus 1. Oh, sorry, I'm off screen. So this is the last one, once again. This equation here with the minus 1 and the 2 and no further minus 1, this looks like this. But for all previous ones, or actually this is equation, no, this is equation I. That's fine. Oh no, that's equation I minus 1. So it's equation I minus 1. For the first one we get the second, from the second we get the third, from the I minus 1th we get the ith. But we can do this up to I equals k. And now this is now the kth equation. Looks like this. And we plug in this formula here. So now again we take this formula here and use it in both cases. And then we get minus k minus 1 x1 plus k minus 2 on that here plus 2 times kx1 minus k minus 1 equal 0. And so this guy here is actually, so this is now an equation which just contains x1, and we can solve for x1, but first, so if we clean up what's happening here, so minus this and together with that and stuff, actually we see that this is equal to k plus 1 x1 minus k. So this has to be 0, and hence we see x1 is equal to k divided by k plus 1. And we could write it differently by doing plus 1 minus 1 over here. This is in 1 minus 1 over k plus 1. Okay. And yeah, this shows that this entry is correct for I equals 1, and if we plug it in into this here, it also shows that all the other entries here are correct, all these ones. If you plug this value for x1 here and do the math, you see that actually x2 is 1 minus 2 over k plus 1, and so on and so on and so on. Shows x star equal to with this here. So we plug this in here, and then we get the formula for the x stars. Okay, that is that. So we have this already. Now we need to calculate the minimum value and the norm. Okay. So calculating the minimum value. That's it's just calculating. It's so f car k star is equal to f k of x star, and we now have the formula here. And actually we can make it our life a little bit simpler, because we know that this here is L over 4, 1 over 2 dx star 2 norm squared minus ei x star. And we also know that this guy here is the same as this I x x, so I x star x star. That's the thing. And we also know by our construction here, the x star solves ax star equals e1. So this here is actually E1. So we don't have to calculate that much, right? So what do we see? We see that this is L over 4 times 1/2 this inner product minus the inner product. So it's minus L over 4 times 1/2 E1 times X star, and this is now minus L over 8 times the first entry in X star, and the first entry in X star is just 1 minus 1 over K plus 1. And if I'm not mistaken, that was our claim, right? That was our claim here. Just the minus signs arranged differently, but that's what we wanted to show. Okay, that was faster than expected. And now what is left is to estimate the squared norm of the minimizer. So this is just we sum from I from 1 to n over the ith entry squared. And this is then just, so only the sum only goes up to k, because after k all the entries have been 0. And the entry here is 1 minus I over k plus 1 squared. And now it's evaluating this sum. Actually, it can be evaluated exactly. So how do we do that? We do that by expanding the square. It's 1 minus 2i over k plus 1 plus I squared over k plus 1 squared. So it's just expanding the square. And so we have to evaluate 3 sums. So the first one is simple. It's just we sum the number 1, k times. This gives us k. And then we have this sum here. I goes for, oh no, sorry, I want to write it differently. I want to pull out the 1 over k, or the 2 over k plus 1, 2 over k plus 1, times the sum over I from 1 to k over I, plus 1 over k plus 1 squared, and we sum I from 1 to k over I squared. So you see, we only need the sums over the i's and the I squareds. Yeah, that's the famous one here. Especially famous in Braunschweig, because there's a story about Carl Friedrich Gauss, who has been said that he was been able to calculate something like this when he was in elementary school at the age of 9 or something. Now, anyway, this evaluates to k times k plus 1 over 2. And for this, we only show that it's smaller equal k plus 1 over 3, to the 3 over 3. The estimate is not that hard. Probably I would like to add, because we need the exact sum later on here, this is enough. Actually, it holds that the sum over I squared, I from 1 to k, of course, there's an exact formula for that, and the formula is k times k plus 1 times 2k plus 1 divided by 6. So we could also plug in this here, but then the expression would just get a little bit more complicated, and for us this is enough. So why is this enough? This gives us here k minus, and then this here cancels nicely, this 2 cancels with this 2, the k plus 1 with this, it's just minus k. And oh no, there's not equal, there's no bound, plus k plus 1 squared over 3. That's what he wants to show. Okay. So, okay, we could also plug in this estimate here, but this doesn't make it any better. So the important thing here is, oh no, sorry, that was wrong. The squared, sorry. There's a k plus 1 to the 3 here, and we divide by k plus 1 to the 2, so this one here is gone, and this is better because this is what we claimed, and not with the square, sorry. Okay, so now we have all the info available about our bad function that we needed. The info was, this is how the minimizer looks. It has only non-negative and non-zero entries in the first k entries. That's the minimum objective value is slightly negative. Getting more negative the larger k is. And we also have an upper bound for the norm of the minimizer, or one minimizer actually. It's not unique, it's only one of them. Okay, so we're getting close to the end actually, but we only have 2 short results to prove. So the next lecture will give you then the lower complexity bound, but now we collect a few more results. So we have all the info on the function that we needed. Yeah, the function has, we know the minimizer, we know one minimizer, we know the Lipschitz constant, and of course we know the minimum value, and we know the norm of this minimizer. Okay, so now we need to know how first order methods can perform on this function. 18.3. So if we have a p, which used to be k, but for now I use p here, because I also want to use k in this lemma. X0 is 0. Then every sequence xk generated by a first order method fulfills that the xk is of the form a lot of stars in the beginning, zeros in the end, and these are the first k entries. So the same as before. The objective is like that if you start at 0 and iterate, and I forgot the bound for k. So there's something missing here. We need k smaller equal p. So up to that point. For fk, so sorry. Sorry. I have to clean this up. So we choose a p between 1 and n, and we want to apply a first order method to fp. Okay, and then do k iterations, but in k stays smaller than p. And then this is fulfilled. Okay, sorry. So this p here now shows these how long this D matrix is, so how many non-zero entries are there in the D matrix, or how many non-zero rows or columns. And if we do iterations up to the number p, then we see if we start at 0, and actually the 0 should have been an index like that. Then we'll have this popped here, and that's actually not so difficult, because the only thing which we needed to recall was that this is now L over 4 A times X minus E1, and this was this matrix A which only had entries in the first P columns, but also so this A is of the form we have numbers here, here and there, and this is P, this is zeros here, and only 3 diagonals have non-zero entries. That's the important thing. So for example, we see that in x0 this is just this is 0, this is just L over 4, so minus L over 4 EI. So our first order method would give us an EI which is a multiple of that, and that checks out. This only has one entry in the first, only non-zero in the first entry, and everything else is similar. So now by, well, since A is tri-diagonal, so you can read this, what I want to say is tri-diagonal, which means only the diagonal and the first one above and the first one below have non-zero entries. You see, if you multiply A by something which only has entries in the first, let's say 5, only non-zero entries in the first 5 entries, you multiply it by A, it may happen that the 6th get non-zero but nothing more. So the claim follows. So that's just it. So if you multiply some vector which only has non-zeros in the first k entries by this a, you may get another entry in the k plus 1, k plus 1th entry, but nothing more. This comes from the diagonal over there. Okay, that is that. And the last claim for today is, I call this corollary 84. If you have xk with k up to p initialized with 0 and xk is of the form only non-zeros in the first k entries, then you have that the function value of fp at the k is larger or equal than the objective value of the function fk. Okay, so and the why is that? Because of the form of the xk, let's call this here star. So because of this star equality, we have that fp of xk is exactly the same as fk as xk, because kind of xk doesn't, or the zeros here doesn't play a role if you form fp. Right, so these are then the same, nothing else. So the objective function, maybe have a look at this again. Where was it? Here? No. Yes, number 3. Oh, there. No. There it is. Still no. Here. So that's the objective function with this, and if you now see if you plug in xk into fk and then have a look what happens if you increase the k, then you increase the number of rows here, but it doesn't matter if you increase the number of rows because here only there's zeros coming in the xk. So that's also another important observation. So if you increase the index of the function, which means you add more non-zero columns to the d, it doesn't matter for the objective value as long as the x only has zeros in the last entries. So this is also, of course, larger than the best value. It's just some value. It's larger than the best value. Okay. So it seems like we still have 10 minutes, but I think this was hard enough for today. Maybe we go through what we've done once again. And then that's it for today. So maybe I just sort my notes here for a second and then we go through it once again. It's actually a little less material than last time, but still a lot. Okay. So, and then the question, how did you come up with that values? So maybe it's already clear. If not, please ask again. I try to answer them. So, maybe we could also go through the lecture notes. I don't know if this is of any help. So probably it's a little too small, right? Let's go through what I've written here on the paper. So the first thing is this lower complexity bound for the class of only convex and Lipschitz functions. And we've seen that if we have a k smaller than the space dimension and allow us up to that number of iterations, we can't guarantee anything more than being small. We can't guarantee being smaller than this in the end. And this here scales like 1 over square root of k. Okay, and this is kind of what one should expect for subgradient methods that in the end, so that they decay like 1 over square root of k. Okay, so the proof was not too difficult. Well, it was probably not so easy, but it was mainly technical. Yeah, mainly technical. But the general idea is that you try to come up with bad subgradients such that these xk only accumulate value non-zeros in the first entries. And the same idea with a totally different function then works also in the smooth case. In the smooth case, the function I copied from the book by Yuri Nestorov, Introductory Lectures on Convex Optimization, looks like this. I prefer to write it in matrix notation. It's norm of d squared over 2 minus the first entry of x, then only scaled by L over 4. With this difference matrix D here. So we calculated everything. This actually has Lipschitz constants smaller than 1. We could calculate the minimizer explicitly by some nice recurrence. So we could really solve this system of equations here. And we could also estimate or also calculate the norm squared of the minimizer, and we're going to need that in the end. So this took us some time. This was mainly calculations. And then the next important step, and I was probably too brief about this, is that because of this tree-diagonal structure here of A, it's also the case that if we initialize with 0, that we only accumulate entries in the first, non-zero entries in the first k entries. So and the reason is that we have this E1 here. We have this E1 here, which gives us that in the first iterate, we can only get an entry in the non-zero in the first entry of x1. Because if you plug in 0 here, then that's the direction you need to go. Okay, and from that point on, if you assume that you have a value, an xk, which has entries in the first k and non-zeros in the first k entries, and then you multiply by a, you get another non-zero entry in the k plus first one. Another non-zero in the k plus first entry. So it only fills up from the beginning to the end. And then finally, by also the structure of the problem, that we see that if we kind of change the problem for a larger p, the objective does not change if the entries of the k are 0 in the end. That was also an important point which we're going to need in the next lecture. Okay, that's what a lot of stuff, and on top of that it was mostly theoretical. And it's going to stay theoretical for the next lecture, where we're going to finish the worst case analysis for smooth L-smooth convex optimization, and also for strongly convex L-smooth. But in the lecture after that, we're going to derive and analyze algorithms to solve the problems and see how good they perform in comparison to the worst case bounds. Okay, so that was probably not the simplest lecture. I hope you got something out of it. In case something is still open, please ask. But also there's these exercise classes coming up. 2 of them, one tomorrow afternoon and the other one on Friday, where you have the chance to work on exercises. Okay, good. So thanks for listening, and see you in chat or next Tuesday.